Okay, so this screencast is going to take you through how to calculate as well as what information can you get from the KEQ, which is the equilibrium constant, for an equation. So what information can be gained from calculating or knowing the KEQ for an equation? So we're going to be able to make some predictions. You have to know how to calculate equilibrium constants before you can really analyze them. Now, I am not going to actually make you guys calculate a KEQ, but I am going to have you set up the problems. So the way that it works is you look at kind of any basic equation. Now, not every equation has two reactants and not every equation has two products, but this is just kind of a basic two reactant, two product equation where A and B, capital A and capital B are the reactants, capital C and capital D are the products. And you'll notice down below right here that we are going to take the concentrations, which would be the amounts, the moles per liter, the concentrations of these reactants and multiply them together. So the concentration, that's what the brackets mean, concentration of A times the concentration of B, and that's going to go on the bottom. Reactants go on the bottom. The concentration of C times the concentration of D, that is going to go on the top. And then you'll also notice that we have superscripts in here, exponents. The exponents are actually the coefficients in the balanced equation. So if there was a 3 in front of this reactant, then I would have this reactant to the third power, the concentration to the third power. If there was a 2 in front of this reactant, then I would have this one to the second power. If there's nothing, then it's an understood 1 and you don't put anything there. So that's kind of the basic setup for any equilibrium reaction. So let's look at this for an example, looking at an actual reaction. This is also the one making ammonia. So we've got nitrogen gas plus 3 hydrogens gives us 2 ammonias or 2 NH3s. So you can basically divide this reaction into 2 parts, one being the forward reaction, the other one being the reverse reaction. So our forward reaction is the N2 plus 3H2 gives us 2 NH3. The reverse reaction is the product going back to the reactants. So the rate of the forward reaction is going to be N2 to some number, which in this case is going to be 1, and H2 to some number, which is in this case going to be 3. And the rate of the reverse reaction is going to be the constant times the concentration of the product to some number, which in this case is going to be 2. So the rate equals the rate. The rate of the forward equals the rate of the reverse. And so if you have the rate of the forward over the rate of the reverse, that's going to tell you your equilibrium constant. So that's just a little bit about where we get these numbers from. But the main thing is just to remember that the forward reaction, the rate of the forward reaction, the rate of the reverse reaction, in terms of their products is what you're looking at. So you're going to have products on top and reactants on the bottom. So using our equation, that's where I said with the NH3, the concentration of NH3 to the second power divided by the concentration of N times the concentration of H2 to the third power. And you notice that because we only have one product, there's only one thing on the top. If we had 3 products, there'd be 3 things on the top. If we had 1 reactant, there'd be 1 thing on the bottom. So it just depends on the reaction. And the KEQ is constant at a constant temperature. So if I change the temperature, I change the equilibrium constant. Think about that. Temperature can make reactions occur faster or slower. So, of course, that's going to change their equilibrium concentration points. It's going to change where they become that kind of magic balance at. So, writing the equilibrium constant expressions can only be written after you have a correct balanced chemical equation, because remember we have to use those coefficients as superscripts or as exponents. Each chemical reaction has a unique equilibrium constant valued at a specified temperature. The brackets represent molar concentration, so moles per liter. All equilibrium constants are shown as unitless because if you have moles per liter divided by moles per liter, you end up canceling it out. Only the concentration of gases and substance in solution are shown. The concentrations for pure solids And liquids are not shown or not included because they're not really participating in that equilibrium. So writing an equilibrium expression, if we use all of the rules, no solids and liquids are present in this reaction, so we don't have to worry about leaving them out. We're only going to deal with gases and aqueous stuff, and in this case, they're all gases. We know it's a reversible reaction, so we know we're not going to 100% product completion. All the reactants and products are in the expression. The numerator term is the products, so HF, the concentration of whatever hydrofluoric acid is to the second power, divided by, that line should be up here, divided by the concentration of hydrogen and the concentration of the fluorine. So each term contains an exponent identical to the corresponding coefficient. So you notice that these do not have coefficients in front of them, so therefore they do not have exponents. But this one has a coefficient in front of it, so it has the exponent. Looking at this one, here's another one to go through. It is a reversible reaction, but since MnO2 is a solid, we leave that out. And water, the liquid, is a product, but it's negligible compared to the solvent water, to the water of this right here that actually has the stuff dissolved in it. So we leave this one out and we leave the water out. We are concerned about the concentration of Mn2+, so the manganese ion, as well as the chlorine gas. And you notice those have no coefficients, so they have no exponents, divided by the concentration of hydrogen to the fourth power because it has the exponent of 4, and then times the concentration of chlorine, and it's to the second power because it has an exponent, or it has a coefficient of 2. So that's how you would write the KEQ, or the equilibrium constant, for this reaction. So what does this value mean? The reversible arrow in a chemical equation indicates that there is an equilibrium that exists, and the numerical value of that equilibrium constant will tell you the extent to which reactants have gone to products. So by looking at the value of KEQ, I can tell, or you can tell, what's favored, products or reactants in that reaction. So if your KEQ is greater than 1 times 10 to the third, so if it's very large, that would be 1,000. So if it's bigger than 1,000, that's a very large value of KEQ, indicates that the numerator is much greater than your denominator. So that means you are going to mostly products. Your top number is going to be huge compared to your bottom number, so your concentrations of products is going to be way higher than your concentration of reactants. And so at equilibrium, mostly products are going to be present, so this reaction would favor products. If your KEQ is less than 1,000th, like 0.001, that's a very small value for a KEQ. That indicates that your numerator, the product, is a really small number, and your denominator, the reactant term, is a really big number. So you're taking a small number divided by something big, you're going to get less than 1. At equilibrium, that is implying that because there's so many more reactants, that's what's favored. That reaction is going to be one that's not going to go to products very easily, and so that might not be the ideal reaction you want to do if you're trying to make a certain amount of product. If the KEQ falls between there, then the equilibrium mixture contains significant concentration of both reactants and both products. And it can kind of go anywhere from like 60%, 40%. It can be a 50-50, but for the most part, you can look at that KEQ value and get a pretty good idea what's favored. Products, reactants, or both. Are they more in the middle? So calculating the equilibrium constants, like actually getting a number for them. A reversible reaction is allowed to proceed until the system reaches equilibrium, until your concentrations are not changing anymore. That's what equilibrium is. The amount of reactants and products are no longer changing. You can analyze the reaction mixture to determine the molar concentrations of each product and each reactant. This would be where a titration with like an acid or a base would come into play at. We are going to do titrations in the next unit, but you use the known concentration of one solution to calculate the concentration of an unknown. So in this case, here's our equilibrium between NO2 and N2O4, and you can see that over time the NO2 decreases and the N2O4 increases until we reach a point where they're not changing anymore. So here's another example. If I take HI and I place it in a sealed container and I allow it to come to equilibrium, the reaction that forms is the HI decomposes into hydrogen gas and iodine gas. So if I were to just write the equilibrium expression or constant expression for that, I would have my products over my reactants. So the concentration of hydrogen times the concentration of iodine, and there's no exponents, divided by the concentration of hydrogen to the second, or HI to the second power. So if I knew, or I was able to calculate how much of these materials I made, like what their actual concentration is, moles per liter, rather than just looking at moles per gram or grams, I'm now looking at moles per liter. I can calculate how much I started with and how much I ended with, and then calculate how much I started with of the products and how much I ended with. And then all you have to do is just plug these numbers in for these values. So for HI, I'm going to plug it in as 0.54 to the second power. For the hydrogen and the iodine, they're both 1.72, so I'm going to plug those concentrations in, multiply those two, and then divide by 0.54 to the second power, and I get 10.1 or 1.0 times 10 to the 1 as my equilibrium constant. So what does that tell me in terms of the equilibrium? That tells me this number is clearly greater than 1. So I'm definitely this reaction is definitely gonna go towards products, but I'm not at that like 1 times 10 to the third value to where it favors all products. So it's gonna be somewhere in the middle. And you can see here it's somewhere in the middle. We are still retaining some of the reactant. Not all of it has gone to product, but we do have more product than we do reactant. And that's what would be expected by a value of, you know, higher than the 1 times 10 to the negative third. So the next point, or the next goal for us, is to be able to look at a reaction that's in equilibrium and then make tweaks to it to get it to make more reactants and make products. Get it to do what we want it to do rather than just letting it stay in equilibrium. And that's where Le Chatelier's principle comes into play at.